Yeah, I just want to show that table in the book on which lens. This is the one. This is for convex lens, right? So first the object is at infinity. Okay. So image is forming at focus, and I'm bringing the object slowly nearer to the lens. So it's beyond this focal point, or sorry, beyond the center of curvature. Okay. So the image will form between. So yeah, here at center of curvature, the object is also forming. Image is also forming at center of curvature. Both are same size. Okay. So as I bring the object nearby, U is going down, so V will go up. So you will get enlarged image. Before that, U is more, so you get diminished image. Highly diminished point. So this corresponds to magnification being 0. This point size, no. Size of the point is 0. Image object will have some finite size. So this corresponds to magnification being 0. After the magnification is slowly increasing, here the magnification is 1. After the magnification is greater than 1. Infinitely large, highly large. And here it's enlarged, but it's virtual. So when it crosses the focal point, this is between focal point and the pole of the lens. It's very close to the lens. They will become virtual image. Okay. So here it's the light will diverge. You're showing the very diagram, right? Here, here. See, this is the focal length, right? So here I'm placing the object within the focal length, close to the lens. So here, if you apply the same rule, ray parallel to the principal axis after refraction passing focus F2, and ray which is passing to the center or the pole will go straight. So actually, if you look at these two rays, only when this object comes within this focal length, it will look diverge. They are going far away, right? Before that, here these rays are converging. They're coming together. Here also they're coming together. Here also these two rays are coming together. Only when you go within the focal length, inside the focal length, these two rays which are coming out are diverging. Okay. So since they're diverging, they will not meet here. So you have to project it backwards to meet it here. So this is the virtual image. That happens if the object is within the focal length. Okay, but for concave lens, it's always diverging. Here also, if you take these two refractors, it's going away, it's diverging. From infinity also diverging. This is the only possibility, irrespective of whether it gives the object large distance or here or less than the, between focal and the center of curvature or within the focal is always the light rays which are coming out are diverging. So once they're diverging, they cannot form image on this side. So I have to project it backwards to get the virtual image. So for concave, it's always virtual. And with convex lens, only at this within this focal length, virtual. So in some sense, I can say a convex lens where the object is placed within the focus in the pole that is close to the lens is like a concave lens. In sense, it's diverging and it forms a virtual image. Okay. Yeah, let me finish that table. So that's what they have said for convex lens. Start from here, bring the object near to the lens, and you'll see how the image is changing. Okay, so it's not complicated. For concave lens, one is at infinity, the image will form at focus, but it's a virtual image. But after that, when I bring the thing close together, it does not matter. It's always diverging. So the image is virtual and erect. So they have shown me two figures for concave. This one is at infinity, another one is anywhere. Wherever you place the object, the ray diagonal is exactly same. It's already diverging. So the image will be like this. Here the image actually diminished. Once I get nearby, it will start getting enlarged. One more thing I want to say is this lens formula, this 1 by u is 1 by v to the 1 by l. So for convex lens, the object is here, I'm trying to move it here. Okay, so that means that minus u, magnitude of it is decreasing. Or I can say minus u is decreasing because u is negative. I don't need the outside. So this quantity, as I move this object nearby, is decreasing. So if you look at this term, first term, the whole thing, so it is going up as I move the object close to the lens. Okay, and this focal length is fixed because the lens is fixed. This is a fixed quantity. So since this first term is going up, the second term has to go down. So when this goes down, V has to go up. Okay, so as this object comes closer, initially the image will be V is okay, yeah. V is here, and after that the V will move away. The image will move away. The object is getting close to the lens. And when this happens, the magnification, which is V by U, will also increase. Okay, so this is true until I get to the focal point. So if you go beyond the focal point, V will become negative. Once I cross this focal point, so between F and the pole, V is negative because the thing will start diverging. I have to project it backwards to get the image here, virtual image. So V is negative. So in that case, if I try to still move in this direction, the magnitude U will decrease. So the first term will increase. So for this has to, yeah, U will, V has to increase, right? So V has to increase means V has to become less negative. I'm any confusion. Okay, I'll write like this. Okay, for this point, I'll rewrite the lens formula like this. It will be 1 by minus V minus 1 by minus V equal to 1 by F. So here, when I try to move this object from this point to this way, minus U is decreasing. So the first term is increasing. Okay. And the second term also has to increase because it's a first term minus the second. This is my second term. And this is my first term or the first term. And there is minus sign in between. So once this is increasing, this also has to increase. So that means that minus V to decrease. Okay. So once I move this one, even V will get closer to the lens. So this plane mirror you can think as a spherical mirror with a radius of curvature being infinite, or even yeah. This is a spherical mirror. Okay, So there's got some radius of curvature. So we make this mirror like this, like flat. Okay, here the radius of curvature has increased. So R2 is greater than R1. This is R1, this is R2, this is R. So if you make it more and more flat, so it will become like this. Here the radius of curvature, this of a plane mirror, this is equal to infinity. So I can think plane mirror as a spherical mirror. It is spherical mirror with R equal to infinite. Radius of curvature is infinite. And R is 2F. So that means the spherical, that means I can say the plane mirror is a spherical mirror with focal length as infinity. Or I can say plane mirror is a mirror with whose focal length is infinite. So plane mirror is a special case of spherical mirror where the radius of curvature is infinite or the focal length is infinite. And ray diagram of prism.
Sir, I have a doubt, sir.
Yeah.
Sir, is atmospheric refraction in human eye lesson an important topic, sir?
Atmospheric, no.
Okay, sir. Thank you.
You should know the prism thing. And also a rainbow, it's being formed by a spherical droplet of water, right?
Okay, sir.
Yeah. So this is the prism and this is the glass and this is air. So since glass is denser, so when it enters this, this is normal. So this is the light ray. So when it enters, when instead of going straight, since the density will go towards the normal, go like this. So at this point, there's another normal here. So instead of going straight, we'll go away from the normal. So this angle of incidence, this angle of refraction, R1 I can say, and this is R2, second angle of refraction, and this is the emergent angle of emergence. So in this interface, the refracting index of glass with respect to R is sine I by sine R1. This angle is R1. So at this interface, I can write refracting index of the second image is air with respect to glasses, sine I sine R2 by sine E R is on this emergence. So sine E. Okay, so this is greater than 1 because glass is denser and this is less than 1. So this means that angle I is greater than angle R1. Here R2 is more compared to E. Sorry. E is more. Compared to R1. Because in rarer medium, the angle will be more. We go out from the normal. So this is I is in air and E is in air. So the angle will be more. R1 and R2 are within the glass, so the angle will be less. Okay, and rainbow formations due to a spherical droplet. The light ray incident on this one. Again, there will be normal here. Instead of going straight, we'll go towards the normal. Okay, and here at this point, with the angle of incidence, here at this point, if it's given the critical angle, you get total internal reflective. Come like this, and then here again there will be refraction. This is the normal direction. So instead of going straight, we'll go like this. Yeah, this is the one. So there is one refraction here, and after that it gets split into colors. There is dispersion. So first is refraction, and then there is dispersion into constant colors, and here there is total internal reflection. Okay, and again here is refraction here. So here you get the colors. So we can say there are three processes that are going on in this rainbow formation. First is the refraction in this phase, and there is dispersion where the individual colors are getting split, and here is student reflection. The peak process indicates the rainbow formation or involved in the rainbow formation. Concave mirror, yeah, same thing. That in that book, the table, there was no put the table for concave mirror. This one. First, the object is very far away. The image will form at focus. And then now we are bringing the object near to the mirror. So it's beyond C, between infinity and C. So image will form here and it's diminished because U is large, V is small. So when the object is at center of curvature, image is center of curvature. So since here the magnification is 1. After that, U has decreased and V has increased. So V by U, this is the magnification enlarged. Okay. And at F, the immediate form infinity is highly enlarged. And between this one, the be enlargement will be virtual. Yeah, for drawing radius, we can use both. One is this one, parallel specific focus. One which is passing the center well and hitting the pole retrace back because it's instead of the normal. Okay, this line is normal line because it's passing in the center. So whatever light goes to him is hitting along the normal, it will come back in the same path. And one more ray you can consider, which is the ray which is hitting the pole. This one. This also used to target ray over. The light is hitting the pole will get reflected back at the same angle. Because this is a normal. Okay. So angle of incidence should be angle of reflection. So it will come out symmetrically. So whatever light that hits the pole will get reflected symmetrically. So if I is the same angle. So this is 5 degrees, this is also 5 degrees. This is true for concave and also convex. See, whenever the as lens also, here also the reflected light, whenever the reflected lights getting towards each other, it will converge at a point, give a real image. Only this object is placed within the focal length, the reflected lights, this one and this one, they are divergent. So once they are divergent, they won't form any real image. You have to project it backwards to get a virtual image. Okay. This is similar to lens. And for convex mirror, one is infinity. After that, for convex, like this convex, no convex mirror, the reflected light is always diverging. Okay, so you cannot get real image, irrespective of where you place the object. It's always virtual image because the reflected light is this one and this one, these two lights. They're diverging, so you have to project it backwards to get the virtual image. So that's the case. We just put 2 cases here. One is anything, another is there is question about where you keep the object is always the diverging reflected rays. Once the light rays are diverging, you have to get a virtual image only. In the case of mirror, it's diverging reflected light. In the case of lens, it will be diverging refracted light. So whenever the light rays are diverging, that's reflected or refracted, you cannot have a real image because they won't converge. The one way to make it converge is to project it backwards and then make it one. That will be a virtual image, not a real image. So I think with this you can do well. Focal power is 1 by F, and the unit of power is diopter. Important thing is focal should be in meters. If you put in centimeter, the answer will be wrong. Okay. To get the power in diopter, you have to put focal in the meters. So if they are given in centimeters, you have to convert to meter. So they would ask the person has got to see, could I have a near point at 25 centimeters? Okay, but he says this person has got a near point of 70 centimeters. You have to suggest what specs he has to wear to correct it. So can you do this problem? For a good eye, the near point is 25 centimeters. Okay. Like if the object is here, the image will form here, but this is a eye with this defect. So for this object with 25 centimeters, the image is forming beyond the retina. And in this particular case, they are given the near point is 70 centimeters. So how do you correct this defective eye? By using what specs? Okay, so whatever is there at 25 70 centimeters, it should appear as if it's at 25 centimeters. Okay. So you, uh, yeah, okay. So shall we close?
Yes, sir.
Yeah,
Yes, sir.
yeah,
Yes, sir.
yeah. Okay, fine. Then all the best. Good night.
Thank you, sir.
Thank you, sir. Good night.
Yeah,
Thank you, sir.
yeah, fine.
Thank you, sir.
Thank you,
Good
sir.
night.
Good night, sir.
Thank you, sir.